Thank you very much for attending. So I am Arnaud Bailly. I'm a software developer. I've been for the past 20 years or so.
I'm Yann Schwartz, software developer as well, for pretty much the same amount of time.
And what we will be talking about is behind this kind of mysterious title, OneLog. It's the idea that the log and the log of all the things that happen in the system is your most valuable asset when you are actually running the system. And I come more from a developer and application and coder perspective, and Yann comes from a big data operations perspective. So the question is how we make sure that when we design our systems, when we code our application, and then when we run it, we make the most out of the logs that we get.
So we take this problem in a threefold way. We first posit that really what's making up your system is basically everything your system does or processes, including the logs. So to be able to actually make some use of all this information that comes out of your system, which is not its main business, how do you shape the logs to be useful? And once you have this, you can start having fun with the logs and actually have the logs as a mean to make your system better and more observable. So this is the generic diagram of every application ever. You can think of your system as taking inputs and doing outputs, but this is a naive way to say things. That's like you have a specification, you write the code, and it works. But what really goes on in a system that's live, that actually ends up in production, is that it keeps emitting a lot of peripheral information, which is not what it's supposed to do, mainly, which are logs, monitoring, events, trace, whatever it does, files it writes, which we call accidental outputs. And also, you end up having needs for endpoints that make it possible to change the behavior of your application over time. It could be beans in Java, it could be a REPL rappelling directly to your application to observe it, to change its behavior, which is not the main flow of your application, but is entirely part of your application and one of the more important parts. And this we call the operation plane. You have the functional plane, which is why you're supposed to be paid for, to do actual processing with your system. But for this to work, you need an operational plane, which is both data that is emitted by your application and also ways to change the behavior of your application, the runtime behavior of your application. The most fundamental thing we deeply believe, is that you should look at your application, of course, look at the input and outputs, but also consider everything that your application does to the world. And when you look at the sum of all those three parts, you have what your system actually is. You have the true model of your application. Everything else is basically an abstraction, some mind view. What really is, what's the cake in production is some Larsen effect, is the sum of it all. So once you see that, you have to embrace this and make that accidental output everything that's basically an afterthought, stuff that are lost in files somewhere or appears on a web interface somewhere. Try to think about the best way to make it available and usable.
So this is all probably very abstract, or I mean, I don't know if it's kind of obvious or abstract nonsense. We'll try to make it a little slightly more concrete with an example. This is a small demo, kind of trying to illustrate what we're thinking. So this is an image I copy-pasted from some random library over in the web, and this is a typical log that you would generate, usually. what we're saying is that this is wrong, basically. This is totally unusable. There are a few issues so first of all, the syntax of this thing is totally unknown or irregular. There are brackets around it, whose meaning is totally random. You have the log levels. You have this piece of text, which is meant for human consumption afterwards. So all this is totally irregular. So one of the steps, and one of the steps we want to illustrate in this presentation is that we need to generate logs primarily from machine consumption, given the scale at which we generate them. We'll go through. So we have a small application. Can you see it at the back? Yeah. We have a small application, which is in the typical old-fashioned way, a pet store. I'm not sure how many people remember what a pet store used to be. I see a few gray here, so probably quite a few people. But so this used to be the canonical application from the early Java days.
That's the 90s.
Late 90s, early 20s. So this is a pet store. And this is a pet store. This is a distributed pet store where we have a pet store where you can buy pets, whatever. Not important, not relevant for what we're talking about. And there is a payment system where when you check out, there's a payment system. And this is an application that is written. So the pet store is in Haskell, and the payment system is in Java. And yeah, this is an embryonic distributed system. So if we start this thing a very early stage. And a very early way to run that is to execute the application. So we'll be running our application. No, actually. So we have a small script to run that. This runs the system, and now what our system does, we'll just wrap everything into a driver, which is not important, which just sensitizes the system. And we have a bunch of logs that are generated. And those logs are, well, they go where all logs go. They go into files, which is cool. But now, if you look at those files, then we have a bunch of files here. We have things that get out of stack, and this is a typical log that you will get. Unstructured. You have random strings here and there. We are mixing. So we have all that's happening in the application, both at the endpoint level, the HTTP logs, but you also have what's inside the application itself, the business side. But it's kind of the formatting is totally not structured. Obviously, this is for illustrative purpose. It should be even in a real application, which is it's slightly more structured, but. And then when it comes to Java, it's slightly worse because now you don't even get the abstraction of a single event being a line or being delimited. You get random strings, or not random strings, but you get warnings. So obviously, all those logs are meant for human consumption. So they assume that somebody is looking at them, or somebody is going to grasp them, or to look at them, or to analyze them.
And usually they're so horrible to read that no self-respecting human would read those. So.
And even though this example is a caricature, it's still typical of the kind of application we get and the kind of logs we get out of our systems. So one of the first steps to get to the ideal logs that we want to have is to structure the logs. So yes, I know JSON is probably not the best format out there, but it's there. But at least it's a structured format. So one way is basically ensure that all the logs are actually structured in a machine-readable format. The basic idea, beside the actual format that we are using, which doesn't matter. So we are still logging into files, but those files now are slightly more structured. So we have this And we have everything is written in a JSON file. And now what I can do is that I can get my logs. For example, I can analyze my log, and if I want, I can select something like, well, you know what? I want to get all the messages which have the tag add, and I get structure. I can analyze those logs. This is the data. This is not anymore some accidental output that's been emitted by the system, but it's actual data. And I can operate on that data. I can do stuff with it.
There's only so much you can do with grep, actually. So instead of trying to do ad hoc parsing of any single line of code of string you get, why not actually have something that's parsable in the first place?
And then obviously, as soon as you have structure, then you get into the realms of, yes, but if you want to have a structure, and if you want to analyze that structure, and if you want to understand it, then you need to have a schema, or you need to have a type, basically. So coming from a Haskell background, I like to call it a type. If you want to call it a schema, just call it a schema. Don't throw stones at me if these are not the same thing. Maybe they are not, but for our purpose, they are. And the idea is that each log is actually an event in the system, which has a type, which has a meaning, and this meaning you need to really be able to reap the most out of it. The last stage is that this is fair, this is good, but if we want to get one log, then as soon as our systems start to get their own logging and to log to whatever they can, like files, sockets, descriptors, you name it, then it starts to get problematic because now I have a zillion way of logging. So the next step toward getting to that vision of this one log thing that we want to be able to operate on is really to make sure that you are logging everything into the same channel, the same firewalls, and every event that happened to your system, to your application, or that your application generates should be in part of that log. And so in our case, this includes events that happen to the pet store, to the payment system, but this could also be, we could also say that, well, it's actually important to understand what happens in the host operating system or in the container system that's operating those things. So the idea is that we want to put all those logs into a single channel, into an integrated, like a fire hose where all the logs go and where everything gets dumped together.
So we get the accidental output of our system as a whole, everything from our application, but also everything from what's running in our system.
So what we did was a third stage of our application that we implemented. That now we have an application. We have our application server. We have our payment system running, and now we also have an OS query server running that we query every few seconds. That will generate information about the system that is running on. And so now in the log of our system, so obviously it's not really nicely formatted. We get a lot of garbage, but it's something that we'll talk about later on. But this is fine because we can pick and choose and get what's interesting inside this. But what's important is that we get all information, and we can get the relevant information after the fact, and we don't have to think before the fact, or we don't have to select before the fact what we want to get out of that.
The different colors shows a different source from the logs. So basically,
but this is just for human consumption. So now when I generate, so I'm just stop the system, but when I generate my information and when I generate when I call my system, then I get the various logs I get both the input and output of my system, so what gets input at various layers, but I also get the information related to operational concerns, like how much CPU did I consume, or how much RAM did I consume, or maybe like Docker events, let's say, okay, I'm going to restart my containers, or whatever. And all this is now nicely formatted in a single format, which is, in our case, JSON, that we can actually work on, take as data, and use as a structured data to work with. So this simple example
So yeah, to sum it up, and we'll see from this, which looks like either some brain dead ideas or stuff that are so obvious, there's no reason to talk about it. It's that the foundation to be actually using something on the log. So the most important things, and Arnaud mentioned it, is that don't consider your logs as random strings that are dumped into files. Basically, consider them as messages. And you have this, maybe the saddest thing that can happen to any logging system is string interpolation. You have your template, you have the nice name of your data inside your template, then you pass the values and everything is lost inside a single string, and you lose either the name of your data and the actual content because you'll have to pass it back. So what's important is the template is actually the type of your event, and the values are the values of your record. So the first thing to be able to start doing something meaningful with your logs is to use structured logs. JSON or whatever, doesn't matter, make structured logs. Once you have this, and you saw that we used system metrics as logs, that basically one other thing we posit is that logging, monitoring, tracing is basically the same thing. They're not used or viewed the same way because you have obviously performance problems to actually, trace a million times a second or emit a log. But actually, this can be addressed. But don't keep paraphrasing yourself, saying that I send a message, I log that I send a message, I send a graphic event saying I log the message, and then using use Zipkin span to say that you spend 1 millisecond to send a message. This is basically the same thing. Why should you write 4 lines of code to do that? So you should, as much as possible, say the things once. And your application is not the piece of the process that's running and emitting stuff. Your application is actually a system made of different applications talking together, and also the hosts that are actually running on. So you have to aggregate to put everything that's emitted by your system in a single stream, flow, whatever. I leave the implementation as an exercise. Usually syslog or Kafka are great for that. And something that's really important, we did a little jab at logging levels, which are the second saddest thing that happened to log. The first one being using strings. The second one is debug and trace. Debug and trace is not about debug or tracing. It's about actually saying, oh, I don't care that much. I care about this info, but I'm so afraid there will be too much of it because it's human readable, but I don't want to read all this line, so I'll just forget about it. So basically, it doesn't make sense. Logging.info says, oh, okay, I'm giving you some information, which is, yeah, that's obvious. And one error can be, you can actually argue they're useful. So don't censor yourself. Don't use log debug or log trace. Log them, and then have some intelligence downstream to say what you'll be actually doing with those events. Because when you log, you debug, basically you will keep the information you would need to troubleshoot something would be lost because it was in a debug, or you will add it later. So just don't use log trace. What's important to make it actually feasible is not to take what's coming out directly from this really, really, really chatty logging system, but to have a deep topology of post-processing that makes view, that sends to different storage system and so on. So don't lose your information at the point of emission. You just work with your data later to make something useful out of it.
And one thing that at the application level, or the design of your application level, which is really an enabler for this kind of strategy for saying, okay, now everything is a log, everything is an event. Well, obviously, you can say, well, if I structure my application as an event sourcing system, then basically, yes, everything is an event. And this fits naturally with this vision where we say, I can show you the idea behind it, because now we can say, at the level of my handlers, at the outer layer. The only thing that I do is that now all I have to do is to send commands. So I structure my applications as commands and events, or inputs and outputs. I just use input and outputs, which are more generic here, but this is the same idea. I issue commands. Those commands will be handled by the system and interpreted in some specific way, which is my business logic. And now I can, to log that, the only thing I have to do is that. So with one line, which says, okay, I get my input, I get some output, I will log the facts, and this is part of the log. This is actually the only thing that I will log as part of the application is I got some command issued, and this command generated this output. And by the way, this output has been stored. It has been saved as the state of my application. But I also issued all the logging and all the traces that are needed to really understand what my application was doing at the time. And then you also have logs and tracing at the outer shell, like the API endpoints, or maybe even if you have something else like the container or the orchestrator logic. But that's the idea of how event sourcing can help us as developers to just say, okay, it's now, it doesn't have to be an afterthought. One thing that's really sad about logging is you look at a code base and then you see, oh, it's all sprinkled with log.info, log.debug, log.error, log.whatever. And then worse is that, oh, by the way, if log level is, then do log something. And this is really sad because it just clutters the code. And you don't need that, basically, because obviously you have a pure functional core, and then all the actions that can impact the outside world are logged as commands and as and then you have the additional advantage. Now the append-only log is a natural fit for the storage of the system.
So once you have this system in place, which is actually readable and actionable data for your logs in a centralized way, and with a mean to consume it, you can say, okay, we mentioned append-only log, so you can say, okay, what if what I'm reading is actually a sequence of tokens that I can try to make sense of. So as reading the output, the accidental output of your system is actually trying to make sense of something that's said to you. So using this not only as a metaphor, but actually as a way to process the logs, we can have 3 different levels of operating on them, saying each, it's not a line anymore, it's a message, it's a template with value, record the type. So you see your types as the words of your language, or you can say, how do these words actually interact together, are seen together as a sequence of stuff that happens. So that would be your grammar. What are the rules where you can actually specify how some token should appear before some others? That would be a grammar. And then you say, okay, it's beyond trying to put a grammar over what I'm witnessing, but I'm going to read what's happening and try to make sense of the language I'm reading. What language is this in semantics, syntax, and so on. And we see that it's actually a very interesting and fruitful way to look at your logs. So this sounds a bit far-fetched, but it's actually what we're doing right now, maybe not using these words. But when you look at the state-of-the-art way to actually consume logs in a distributed system, is to have everything in files, have an agent somewhere that reads them and send them back to Elasticsearch and do select on the stuff. Okay, that's a bit better than that, but not so much. So you end up with things like that. And as a human being, actually, you do that because we love language and everything is a language. If it's written, we read this as a language. We see a sequence of stuff that happens, so our words, and we see that there was an error, then there was a service that synced, then an agent failed, and so on. So you consider not the sequence, but the specific events as words. And something that happens a lot, and which is done now, the number here is the number of times it happened. So when you do natural language processing, one of the most simple and very useful way to look at language is just, I'm going to count the words, and see do histograms and do something about it. So if I see that I had 322 times a problem here, that makes sense. So I'm just counting the number of words that happen. So there's something a bit more, that's from, I think, a Datadog, something a bit more sophisticated that's done here, that they try to, the inverse of string interpolation would be string extrapolation. They try to actually kill everything that's variable. So there used to be a date here, there used to be a number, an IP address here. They just canonize everything to be able to count. They wouldn't have to do that if it was structured in the first place, because you would have the name of what happens and all the other would be values in the records. But they say, okay, the word is not the values.
Yep.
The word is actually, so you count, and that's the basic things you do with log. You take any log, you grep error, and you do WC-L, then that's how many errors you had. You're doing machine learning, you're analyzing your log as a language. You just look at the token which are called error. You count, you group, you aggregate, and that's how you do monitoring actually. You count the number of times you said, I did this one action, and that's monitoring. Obviously, you don't do this like this because it wouldn't be that efficient, but if you had something structured and the right pipeline, you could actually do your graphite monitoring like this. So
the next level is maybe we can start to think. So we can operate on the logs at the word level, at the words level. We're saying one event at a time, but maybe we could do something more interesting. So we could maybe try to work on the log that's out by the system, but as a grammar. So saying, okay, we know that there is some grammar there. For example, we say that the logic of a circuit breaker. So circuit breaker is a very common, it's a common pattern in distributed systems. In operating distributed system, you're saying now, okay, if I have that number of errors within 10-second time span, then I should close the circuit. Or I should open the circuit, actually, which is just saying that it's broken, and now you are preventing overloading a downstream system with too many calls, because now you know the system is not working, so there is no value in dispatching all the calls. You just reply that, oh, by the way, it's broken, please call back later. And then you, after some time, you might try to do something like a canary call and say, okay, if this call goes through, then I close again the circuit, and then we get back to same state. So it's a very efficient way to prevent cascading failures inside the system. Every distributed system, in a way, should have that implemented. Should contain some form of circuit breaking as soon as you have several systems talking to each other. So this is very common. This is a generic pattern, and this is a generic way of doing things. So, and one way of saying, if you have your logs, then one way of doing that is say, well, I get all the events, so I can just look at the events happening in my system, so I can just check, okay, oh, there is invalid payment here. I know that I have some logic that says, oh yeah, invalid payment is an error status in my system there. I count them, I get the timestamps, obviously the local timestamps, but I get some timestamps, so I can understand what's the time span between the events. And if I get the actual pattern detected, then I can just break the circuit. So I can just issue some command to the system and break the circuit. So this is basically a state machine. And technically, if you start to abuse slightly the concept, you can imagine that this is kind of what we call a rational transducer, saying that, well, this is something that takes a language as input. So you have a stream of logs, which is all your input. And depending on the input, you can change state and emit more output. So emit a new language. This is a transducer. And this is a very regular way of seeing something like a circuit breaker, for example. You can imagine a lot of patterns like back pressure. And back pressure is something that you can also model that way. Say, well, if in my system I detect that, well, the loads get over 90%, and I know that because now I have the traces of my system inside the log itself, if I get several messages that the load is at 90% for, I don't know, 10 seconds, then I can just set up back pressure and I can issue commands to some components in the system to say, well, stop, please, just stop overloading the system, they won't respond and we want to cool down.
At some point at the keynote this morning, Al Hewitt mentioned that you had to have timeouts which are based on statistics. So basically, this is the baseline of the response time, and depending on this, I will define what's acceptable for my actor to call another actor before issuing a timeout. This is another example of what could be implemented via logs and not an ad hoc system. You just look at the message that says the call took this amount of time, then aggregate this, treating the elements as words, and then using this information, what's the mean, average, or 90 centile, percentile time of the, then send back via the control plane the value for the acceptable timeout for this call. So this is a pretty generic pattern, which is actually...
So this is a kind of cybernetics view of things in the old sense of cybernetics, where you are just trying to understand how to control your system. And so you have your components, very abstract thing, but now the purpose of the runtime, of the idea of having this kind of operational plane and functional plane becomes more obvious. Is that now you can have, well, you can have one component that just does its job, and then you can have a controller on the side that say, well, now I'm going to look at the accidental outputs of my system and say, well, there are some conditions that are not quite right, so I'm going to issue commands to this component. And the nice thing is that you could do that. You could also imagine doing that like an embedded. Like this is a typical revamping of like a proxy pattern or decorator pattern from OP languages or even from general programming, and then get your wrapper. And this wrapper will contain some control logic and can wrap a component, capturing the input, the outputs, and even make decisions potentially even on the input and outputs. And then the nice things with this pattern is that now it can be composable. So you can have your components, your small components and your small controllers being composed, and just because what is actually the medium of composition it's actually the log. So the message is on all the event stream that's sent by your components or your system of systems, and that gets entered into your controller, into your control logic, and then potentially outputting some commands back. Obviously, this is not trivial. Of course, otherwise it would already be done, I guess. But in the case of circuit breaker, the nice thing is that we can actually, in the small system, in the small example that we have shown you, we actually implemented this circuit breaker logic. And this is pretty much generic. Obviously, there are some specialties like, well, what is the event? What is the how do I shape it? But this can potentially be abstracted or generified for the controller. But the idea that this circuit breaker logic can be coded once. It's just a finished state machine. It's a pure state machine, by the way. So it's totally independent of how you get the input and outputs. And potentially you can, in this case, what we do is that we just write some JSON string as a command to the standard input, which is a bit crude, but you can imagine issuing a command to a control port, sending a single message, whatever. And the logic can stay the same. So it's just a matter of adapting the impure part and the IO input-output part, which is the actual communication to the system, just like what we were saying this morning about, well, you have this control logic, and then you have the middleware that's responsible for dispatching the messages, and which is which can be abstracted.
And so the equivalent of general artificial intelligence for logs would be to look at the log itself as a narration, the thing that your systems are telling you. So we see the log streams. The grammar we mentioned previously is not the grammar of everything that's emitted. It's a grammar that isolates what you want to look at. So that would be, I look at 10 error message, in a row, then at something that doesn't work anymore and I emit something. So you actually apply a grammar to an existing language for looking for patterns. So basically you're looking for regular expressions. That's rational expression in a way, but that's a way. What we're trying to do now is what's the actual grammar of the language that is actually emitted. So so that would be looking at what's produced by your system as accidental output, as something that's actually a language, and try to apply natural language processing techniques over there. There are different ways, so basically trying to infer the grammar, trying to make sense of it, trying to see what are the relationships between the different tokens, between the different words. So basically Word2Vec is a very interesting technique, which is basically how to cluster in an unsupervised way. So basically see similarities between words given a context. So they say that they don't really know why, but statistically these words, those two words have relationships together. So nouns will be close because they're used as nouns and they're usually after or before a verb depending on the language and so on. So you have semantics, syntactic properties that are seen by this, and then so basically it's a way to see relationships between words and to see how they relate to each other. So if you apply this to a log, you could see what are the relationships between things that happen in your log. So if you see that often you have, I don't know, you have high CPU monitoring word, and then something that fails in another system, you can say that maybe there's a relationship between two. So what are the similitudes? What are the patterns that things seem to be related? That would be a way to, so another way to see is that what's a language model? A language model is basically what are the, if you look at a statistical way of seeing things, I'm doing a very, very poor and quick definition of what a language model is, but basically is that what's more like, given a token, what's the most likely token to be after it, and how tokens are generated. What's important, so you have a model, so given a sequence of what happened before, what is likely to happen after. And if we manage to have this kind of statistical model from a log, you can see it in two different ways. So there's also the notion of confusion or perplexity, which are not exactly the same, but basically given a model, given what happens in the real world, how different the model and what happens are, gives information. So if your model actually predicts what's going to happen, so see your system as emitting logs. If your model says, looks at the new log entry and says, oh, but basically I already predicted it was that, you don't actually have to emit the log. Because on the other side, you have the same model. You just say, okay, it's what it's supposed to be. So you actually compress your output. And if you have the other way around, so something that says, oh, no, that's not supposed to happen, it's statistically highly improbable, that says, okay, there's something wrong with what's happening with my system because my language model doesn't fit the language that I'm actually seeing. So I would have loved to show you ways to do that. This is actually, this makes sense, and in an intuitive way, I think we could get this, but we have a problem. We have two different problems. You have words, so words are, I don't know, in English, if you have all the flexion and so on, you have maybe 500,000 different tokens. In French, you may have less, or it depends on the language, and so on. In log, if you have unstructured logs, you just sort and do a unique C, then you'll have million and million of lines. So it's like a vocabulary of tens of millions of words. But actually, even if you structure your data and you just look at the type of the event, it's not enough. You need to know what's the type of the event. If it's CPU activity, the CPU activity event with 99 won't have the same semantics than the CPU activity at 1. So basically, you have to find a way to say, okay, this is the raw, but those are my actual tokens. So that's hyperparameters or something that you say how you quantize your words. So that's work to do. And there's also another problem. We get everything. When you think about language, you think about sentence, but actually it's a system with many, many, many people talking at the same time. So it's much, much more like getting into a really crowded room, trying to listen to everything that happens, trying to make sense of it. So you also have to isolate different streams. But it's doable.
Okay, so just to wrap up and maybe have 1 or 2 minutes for questions. So the idea is that if you have structured and typed logs, if you inject in your logs, if your logs are system-wide, and system in the sense of the system you are building and operating, and if you make sure that your logs are unfiltered and contain all the data that represent the actual activity of your system, then you get one log. And if you have one log, then the thing you can do is that, well, you can start to do word statistics. And this is where we are now, basically, mostly in the logging space. And that's already useful, obviously, except that we often don't even have one log. We have a bunch of stuff. But you can also do operations on the grammar. So just defining grammars for logs and then do stuff and even infer things from the grammar or actually take actions from the grammars. And you can even imagine that, and that's something we are actively working on, infer some language out of the system. So this was a question that you can ask if you want, and some related work. So we are deeply influenced by work from Karen Kingsbury in Riemann, which was really a different way to think about logs, and then work by others like the shoulder of giants and all that stuff.